Alright. I want to take a look here at a little bit of review. Graphing, acceleration, a little bit with velocity because we need to deal with that with acceleration as well. So, here goes. This is from page P9 in your workbook. Question 2. We've gone over the graph in class already at the top. But in this case here, I want us to look here at a couple things here. So first, we're going to have a velocity time graph and a distance time graph for this car. Moving at 12 meters per second, it runs out of gas while it's going up a hill. It's going to coast up the hill with a uniform acceleration of negative 1.6 meters per second squared. So if I draw my axes, which I'm not drawing on the screen, I'm going to use a ruler or a straight edge of some sort. Here's my speed, here's my time. It starts at 12 meters per second. Now, I don't have to mark all of the axes, it is just a sketch, but wherever I start here, this is going to be where that 12 meters per second is. All right, so, and then we're going to have a straight line coming on down this way. And this will be 0. Theoretically, I guess if this car is going up a hill, if there's no brakes and we just let it alone, it will eventually continue to have negative velocity and move down the hill. So there we go. Now we want a distance time graph as well. So with our distance time graph, a few things to think about. First of all, that first graph, let me sketch that again real quick. Ooh, got worse. So for our speed time graph, it's a straight line, and it's a negatively sloped straight line because the acceleration is negative. In fact, if we were to calculate the slope of this, if we'd drawn the graph correctly, the slope in fact would be negative 1.6. Over here though, we got to think, what does this look like? It's not going to be some kind of a straight line. If it's a straight line, it means that the car isn't moving. This is not going to slope downwards, because that means it's either it's moving backwards or moving back towards a starting point. In fact, what it is going to do is it's going to, at first, the first second, let's say, it moves quite a long ways. It moves quite steeply. In fact, its initial slope is going to be 12. But then every second, it's going to lose 1.6 meters per second. And so what's actually going to happen is it curves up and to the right. And eventually it's going to reach a flat spot when the velocity hits 0. All right, and at that point it's standing still. And again, if it continues on down the hill, we have something like this. So it slows down, it moves forward, but it slows down, stops, and then speeds up as it moves back towards us. All right. Well, let's look at the second part. What is its velocity 6 seconds after the engine quit? Well, we have a formula for, we have acceleration, we're given that right here. So our acceleration in this case, A, is equal to negative 1.6 meters per second squared. Our V1 is 12 meters per second. That's our starting speed. It says we can talk velocity here because that's what it's asking for. So we don't really know a direction other than we're going to say positive numbers are forward or up the hill. Negative numbers, I guess, would be down the hill. We do know time. That's given to us right here. So t is 6 seconds. And we want to know what is its velocity after 6 seconds. So we want to find v2. And so we start with our formula. Acceleration is equal to v2 minus v1 all divided by t. All right. Now we want to actually solve this thing for v2. So we want to get it by itself. So I'm going to multiply, first of all, both sides multiplied by t. Multiply this side by t. Because on the right-hand side, to start with, we were dividing by t. So we get rid of t on this side. Now I have t multiplied by acceleration is equal to v2 minus v1. And I want to get rid of the v1 on this side, so I'm going to add v1 to both sides. There we go. And that goes away on this side, and I'm left with v2 is equal to a times t plus 1. So let's add our numbers in and solve. Negative 1.6. That's working well. Meters per second squared times the time, which is 6 seconds, plus my v1, which is going to be 12 meters per second. And I'm left here with a fairly straightforward thing to punch into my calculator. So I have negative 1.6 times 6, which gives me negative 9.6, and negative 9.6 plus 12 is equal to a final speed of 2.4 meters per second. That is positive. So it's after 6 seconds, it still is moving up the hill, but it's moving up the hill at 2.4 meters per second. All right. Which takes us on to our next part of the question here. Maybe. There we go. What is the average speed of the car for the first 6 seconds? Now the formula is given to you on your page. So the average speed is going to be equal to I think it gives you VF plus VI, means final plus initial, divided by 2. Okay, this one you can probably do mental math wise if you needed to. VF was again 2.4 meters per second. And VI was 12 meters per second, all divided by 2. 2.4 plus 12 is 14.4, divided by 2 is going to be 7.2 meters per second. Oops. So it averaged 7.2 meters per second for those first 6 seconds. We can find out, now we can actually use this average speed thing because it has uniform acceleration. Okay, this formula actually works for it only because it's slowing down at the same rate. It's not like we gently touched the brakes and then eventually jammed on the brakes. That would be changing acceleration. That becomes a little bit more complicated. All right, so average speed for the car for the first 6 seconds again was 7.2. Okay, now we can use this formula here. V average is equal to distance total divided by time total. How far did the car travel in the first 6 seconds? So we're starting with our formula here. Average velocity, is equal to total distance divided by total time. This is our time. We figured out our distance last time, or we figured out our speed, sorry, last time. And so I multiply both sides by t times t total times t total. That's going to give me distance by itself. So my total distance, or dt, is equal to the total time multiplied by the average speed. The total is equal to 6 seconds multiplied by the average speed, which was again 7.2 meters per second. This is a nice one to put into your calculator, and we end up with 6 seconds times 7.2. And if we hit the right buttons, that makes this whole process easier, which gives us 43.2. My units are going to be meters. Significant digits wise, I would actually have to record this as just 43 because all of my information only has 2 significant digits. So this should be total distance is equal to 43 meters. Lovely. Moving on to part E. How long does it take for the car to have a velocity of 0? So in this case, we have v1, we have v2, we have a, and we need to solve for t. So let's take a look. Our original formula, acceleration, is equal to v2 minus v1 divided by t. All right, we want to get t by itself, so I'm going to have to get it on top of out of the bottom of the fraction, so into a numerator. So multiply both sides by t to start with, and I'm going to get rid of the a over here, so I'm going to actually do this at the same time, or at least show my work in the same place. I'm going to divide both sides by a. Okay, that goes away. Left with an a at the bottom of my fraction here, so time is going to be equal to v2 minus v1 divided by acceleration. Time is equal to v2 again was 0 minus 12 divided by negative 1.6 meters per second squared. Now, just a couple things to look at. First of all, if you go 0 minus 12, that makes pretty good sense that that's going to be a negative number. But I'm dividing by a negative, which means that's good because negative time is not an easy concept to deal with. So let's take a look. Negative 12 divided by negative 1.6 is equal to 7.5 seconds. So it's going to take 7.5 seconds for this car to come to a stop, or at least to reach 0. Now, if we have no brakes, and that's what part F is going to deal with, it's going to start rolling backwards down the hill. All right. So let's take a look at part F. If the brakes do not work, what is its velocity 9 seconds after the engine quit? All right, so let's take a look. We want to find here, we've got, again, this is V1. This is A. Here we have time. We're in fact going to use, we want to solve for V2 this time round. All right, so it's going to end up being the same formula we used on one of the other parts of this question, right? V2 minus V1, all divided by t. That's the formula out of your formula book. I want V2 by itself, so I'm going to again multiply both sides by t. And then eventually I will also add V1, but let's go one step at a time. So TA equals V2 minus V1. Get rid of the V1, so I'm going to add V1 to both sides. And I'm left with V2 is equal to 12 meters per second plus time was 9 seconds multiplied by my acceleration of negative 1.6 meters per second squared. A couple things we're going to notice here, or we should notice here. Anyways, if I take just 9 times 1.6, forgetting about the negative for a minute, that's going to give me a number that's actually bigger than 12. So if I turn that into a negative, now 12 plus that is going to be some negative number, which makes sense, because 9 seconds is more than 7.5 seconds, which means at this point, if there's no brakes, it's rolling backwards. So let's take a look at this here. 12 plus, and then we've got to go in brackets here. On my calculator anyways, 9 times negative 1.6. And we end up with negative 2.4 meters per second. So at this point, 9 seconds after the engine quit, it is rolling backwards down the hill at 2.4 meters per second. Lovely. Now, you have a third question on the assignment that I will let you do.